All right. It's the last lecture of the term. And we're going to take on the thing that makes up everything that we know about. So we're going to do some particle physics here. And particle physics is hard to do in a day because it's to start to understand particle physics, you just have to learn a bunch of the fundamental particles. And so we're just going to do kind of a little introduction to them to give you some sense of how we can go beyond sort of neutrons, protons, and electrons. So this all has to, particle physics has to do with what are called fundamental particles. When can you get to a particle that doesn't have any internal structure, right? So, an atom, we thought was a fundamental particle. It turns out that it's got a structure of protons and neutrons. We thought the nucleus was a fundamental particle, but it has those neutrons and protons in it. And finally, we figured, oh, the protons and neutrons are fundamental, but they're not fundamental either. They're made up of other particles as well. And so at this point, we know of three types of fundamental particles, and you can see that image over here. And you can see that we've got a lot of different particles, right? We've got funny names, right? We've got our leptons and our quarks and our carrier particles. Those are our three big categories. And then each one of those has a set of six or more um, types of particles within that category. But we're just going to talk about the category and recognize that these guys here in family one are the ones that we are most familiar with. As we get into family two and three, we get more and more unstable. And what that means is that these particles only exist for fractions of a second. And so they're not things that make up the everyday matter that we interact with. Now, you may say, wait a second, you think you found the fundamental particles. How do we know they're fundamental? And the truth is we don't. We have limits to what we can see. And in fact, some of these are just conjectured particles that haven't actually been observed. And so it's always possible that we come upon a new particle, right? And in fact, just recently, this model that I'm kind of explaining here, which is called the standard model. It works really well, but Fermilab in Chicago just did an experiment within the last couple of months that suggested that there were physical things happening that weren't explained by that standard model. And so there's always the chance that we'll have to go back. I say we as if I have anything to do with this, to go back and rethink this model. Particle physics is well outside of my area expertise, so we're winging it here together. All right, so let's talk about quarks and leptons first. They are fun to say, so there's plenty of, there's fun there, and they have strange um, qualities too. Like if you look at a quark is a building block of neutrons and protons, and they are the only particle that experience what's called the strong force. And so that's what we think of as kind of the nuclear force. It's the force that holds our nucleuses together, which is really fascinating if you think about it, right? And we got into this a little bit earlier, but if you got a bunch of protons packed together, uh, the electromagnetic force there is going to strongly reject those, right? Those protons want to get away from each other. And so the strong force has to be quite strong in order to hold those protons together. So protons are either up or down, or I should say quarks. And this is the first family of quarks. We have different qualities, including strangeness for the other families. But for the first family, we have up and down. And they have a charge of either plus 2/3 or minus 1/3. And you might say, wait, I thought we had an elemental charge and you could only have a charge of 1 or 0. And that's true because these only exist in triplets. So a quark has to exist with two other quarks. And that means that any given particle made up of quarks can have a charge of either 1 or 0. So you can do a little math here, a little fun little activity, and figure out how many up and down quarks are in a proton, right? Well, we'll need two of these guys for a proton. That gives us a plus 4 third, and the third one takes us down to a plus 3 thirds, which is 1. So there's our elemental charge of 1. And if we have a neutron, we're going to have two of these down quarks, which will give us negative 2 thirds, and one up, which brings us back to a 0 charge. And so those are how the quarks interact with each other to make the protons and neutrons that build up our atomic nuclei. So, like I said, quarks only exist in groups, and in groups of 3, and that total charge of the grouping is always an integer. So that's where that's how this matches up with that idea of having an elemental charge in which it has to be an integer, 0 or 1 or 2 or -1 or so forth. Okay, so those are quarks. Quarks experience the strong force. They are the only particles that experience the strong force. Leptons experience the weak force, which is weaker than the strong force. And we again have 6 kinds of those, and some of them have charges and some of them don't. And so those leptons are here. The most common lepton is the electron, and so that's this fellow here. But also there are what are called neutrinos, and so this here is a neutrino, which is a very low mass particle that doesn't have a charge, but can carry energy if it's moving, just like any other charge or any other particle that's moving. Okay. The neutrino, if you remember, the neutrino and antineutrino are emitted during beta decay. So this guy is emitted during beta positive decay, and the antineutrino is emitted during beta negative decay. Quarks exist on their own, unlike leptons, so an electron can exist on its own. And as far as we know, there's no fundamental particle inside an electron. It's a particle in itself, but again, who knows what happens next year. Neutrinos have no charge, and this is kind of cool about neutrinos. They're very penetrative because they have very small mass and no charge. They are not going to be affected by electromagnetic forces, and the gravitational force on them is going to be really tiny. And the weak force only has a really short range, so they can travel through the entire Earth without interacting with any of the other atoms in the Earth. So essentially, large parts of the universe are transparent to a neutrino. With each of those, so that we talked about quarks and leptons, we have to then talk about that each one of them has an antiparticle. So that's different than the up-down here. An antiparticle has the same mass, but an opposite charge of a regular non-antiparticle. And so you can think about something like the electron. That's our regular particle. The antiparticle is a positron, which has all the characteristics of an electron, except it has a positive charge. Antiparticles are highly unstable, and the cool thing about them is that they annihilate regular particles. So when a particle and an antiparticle come together, they are annihilated. And so here we have this little picture. Here we have some quarks, right? We've got a little up quark and an anti-up quark. And when they come into contact with each other, they essentially disappear and release energy. They can also be created out of a bunch of energy, and you can create one of the positive or one of the particles and its antiparticle. So you can imagine, if we had a lot of these around, we'd be in real trouble, right? We'd all be being annihilated all the time. There are not very many of them on Earth, and it's not entirely clear why that is. Um, One way of thinking about it is that if it interacts with regular matter, they're both going to be destroyed. So we don't, uh, they just don't last very long. But that still doesn't really explain why there isn't a bunch of them. But I guess if the universe is to exist without annihilating itself, we have to have a limited number of them. But it's one of the sort of mysteries of particle physics, sort of the role of those antiparticles. There are some antiparticles on Earth, and in fact, probably some in your body, but they don't last very long, and so they're not they're not something that we interact with in, say, Newtonian physics for sure, um, because they don't really matter to that Newtonian physics for the most part. All right, we have to talk about conservation laws, and the annihilation of a particle and an antiparticle suggests some kind of conservation, right? If anytime you create an antiparticle, you have to create a regular particle, and anytime you destroy a regular particle, you have to destroy an antiparticle. That suggests a conservation of each of those kinds of particles. And in fact, there are a host of conservation laws in particle physics that help us to understand how these particles exist with each other. And some of those we have momentum and charge are concerned. Uh, Angular momentum is conserved. The number of leptons is conserved. The number of quarks is conserved. And all of these conservation laws allow us to think about um, how these reactions are going to occur. So we could go through, say, a beta negative decay, and we could explain how from the left side of that equation to the right side, all of the various uh, particles and um, momenta and charge are conserved in that reaction. Okay, so any kind of reaction, we can't create any of these things out of nothing. And so those conservation laws are just really crucial to, uh, as you get into particle physics, a lot of what you're doing are conservation laws, trying to figure out what's going to happen in this reaction, because we know we have these rules about how particles behave um, and exist. All right, the last category is carrier particles, and we have um, four of those, and well, actually, that's not entirely true. We have four fundamental forces, and these carrier particles are the the apparatus that makes those forces work. So we think, about gravity. Gravity's really odd, right? I mean, it's one invisible, and it's so familiar to us that we don't really think about it. But it's these distant objects pulling on each other, right? How can the Earth pull on the moon when there's no medium in between them, right? There's no thing to pull on. And the carrier particle is the short answer to that very complicated question. Those carrier particles are the exchange medium for these forces. And so each of these forces has a carrier particle or more than one that's associated with them. Some of them we've observed, photons we've observed. Um, the weak force carrier particles, we've observed those, but the gravity particle is a matter of conjecture. And they've made some progress in the last decade or so in terms of trying to observe those. Um, but it's still not something that we've been able to say, oh, there's a graviton. They exchange these forces essentially by exchanging momentum. And so we'll look at a little bit at how they do that. How does a carrier particle function? It functions as a carrier of momentum in moving from one particle to another, like this little photon here, this little wiggle guy. That's our wave packet. That's our wave particle duality, right? This is both a particle and a wave. And it's moving from one particle to another. And we learned that just as mass can be a wave, right? We learned that photons have some momentum. even though they don't have some mass. And so as this photon is ejected from this positive particle here, uh, its momentum is carrying it that way, and the conservation of momentum says, oh, this particle's got to go that way in order to balance momentum in that system here. Then that photon hits this particle, which isn't moving, and it absorbs that particle, but conservation of momentum says that now that particle has to be moving off to the right. And so, like sort of throwing a medicine ball at your friend, when you throw that medicine ball, you sort of move backwards, right? This is you throwing a medicine ball. When that medicine ball hits your friend's chest, your friend sort of stumbles backwards. That's the same kind of exchange of momentum here with objects that are much, 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 much tinier than your medicine ball. And in fact, don't have any mass at all. So the result is a force on both of those particles. So when we talk about the Lorentz force or the static electromagnetic force, that's this process working in particular ways. Okay. Now you might ask, well, this tells us how we can have particles moving away from each other, a repulsive force. How do we get an attractive force? We're going to kind of leave that one, but um, we'll shove it into the wave nature of matter, which answers a lot of questions that are too tough for us to answer in the context of this class. All right, and here's another image. Here's another. If we have two particles moving, as time moves on, they're moving towards each other, they exchange a photon, and then they move off in different directions. Now, you might have asked, we've talked about the strong and weak force and said, oh, its range is really small. The range is really small because these carrier particles that have mass, like they do for the strong and weak force, uh, don't last. They're extremely unstable. And so they can't travel very far before they disappear, or not disappear, but change into something else. Um, and that means that the range of those forces is really limited. Basically, the strong force has a range on the order of magnitude of the nucleus. And so it doesn't really function outside of that nucleus. Um, Gravity and the electromagnetic force don't have those range limits because their carrier particles don't have any mass. And so they have a longer range. So that's a little intro to particle physics, just to give you a kind of flavor of what's out there and some of the kind of cool and crazy stuff that's being done in cutting edge physics. Oh, I left one note there. There's one more note. All right, last lecture. How about that? Woohoo!